Ground rod function testing serves multiple purposes. Firstly, it is used to assess the relative impedances of parallel neutral paths back to the transformer. Secondly, it aids in identifying potential corrosion issues in neutral connections. To perform this testing, one would follow a specific procedure. 1. Clamp an ammeter around the neutral conductor. 2. Clamp the ammeter around the grounding electrode conductor, abbreviated GEC. 3. Calculate the percentage of neutral current using the GEC with the formula percentage of neutral in GEC equals current in GEC divided by current in neutral, multiplied by 100%. 4. Repeat steps 2 and 3 for the water pipe and any other electrodes connected to the GEC. Interpreting the data is crucial. A higher percentage of neutral current in the GEC indicates a lower impedance path for the neutral current. A significant percentage of neutral current in the water pipe may indicate corrosion in the neutral connection to the GEC. This method provides a quick and practical way to evaluate the effectiveness of ground rods and identify potential problems. It is important to consider additional notes. This method requires a sensitive digital clamp on ammeter. The measurement should be taken during peak load conditions for accurate results. It is important to ensure proper safety precautions when working with electrical systems. The benefits of this testing are multifold. Firstly, it helps to identify potential ground rod issues and corrosion in neutral connections. Secondly, it provides a hands-on method for evaluating neutral paths back to the transformer. Thirdly, it can be used as a troubleshooting tool to diagnose electrical problems. When performing ground rod testing, understanding the National Electrical Code, abbreviated NEC, requirements is essential. Section 250.52 A5 addresses rod and pipe electrodes. Electrodes of pipe or rod that are 1. Galvanized steel or iron, or 2. Non-ferrous must meet specific requirements. They shall not be less than 8 feet or 2.44 meters in length and shall consist of the following materials. 1. Electrodes of pipe or conduit shall not be smaller than metric designated 21 or 3/4 inch trade size and were of steel, shall have the outer surface galvanized or otherwise metal coated for corrosion protection. 2. Electrodes of rod of steel or iron shall be at least 5/8 inch or 15.875 millimeters in diameter. Non-ferrous rods or their equivalent shall be listed and shall be not less than 1/2 inch or 12.7 millimeters in diameter. In section 250.53 G, it speaks about supplemental electrode required for replacement. A rod, pipe, or plate electrode shall be supplemented by an additional electrode of a type specified in 250.52. Through 250.52. A8 with a resistance to ground of a single rod, pipe, or plate electrode exceeds 25 ohms. The supplemental electrode shall be bonded to the grounding electrode conductor, electrode bonding jumper, or grounding electrode for the service equipment or system within 6 feet or 1.83 meters from the supplemental electrode. Grounding electrode continuity shall comply with 250.64. C. The requirement in 250.53. G shall be permitted to be waived for existing buildings or structures where the authority having jurisdiction is satisfied that the additional grounding electrode cannot be installed. Understanding impedance is key to interpreting the measurements. Impedance is the total opposition a circuit presents to alternating current. It includes both resistance and reactance. A lower impedance path allows more current to flow. In the context of ground rod testing, a lower impedance path from the neutral to ground through the GEC indicates a more effective grounding system. This is because the ground rod is providing a low resistance path for fault current to return to the source, helping to trip over current devices and clear faults quickly. Conversely, a higher impedance path indicates a less effective grounding system. This could be due to a number of factors, such as a corroded ground rod, loose connections, or poor soil conductivity. In such cases, the ground rod may not be able to effectively carry fault current, increasing the risk of electrical shock and fire. Therefore, measuring the impedance of the grounding system is an important step in ensuring electrical safety. The NEC also provides guidance on the size of the grounding electrode conductor. Table 250.66 dictates the size of the GEC based on the size of the service entrance conductors. It is important to select the correct size GEC to ensure that it can effectively carry fault current. Furthermore, the NEC requires that the GEC be installed in a manner that protects it from physical damage. This can be achieved by running the GEC in conduit or by locating it in an area where it is not likely to be damaged. Regular inspection and testing of the grounding system is essential to ensure its continued effectiveness. Ground rods should be inspected periodically for signs of corrosion or damage. The connections to the ground rods and the GEC should also be checked for tightness and corrosion. In addition to visual inspections, the resistance to ground of the ground rod should be measured periodically. A high resistance reading indicates a problem with the grounding system that needs to be addressed. Soil conditions play a significant role in the effectiveness of ground rods. Soil resistivity is a measure of how well the soil conducts electricity. Soils with high moisture content and high salt content tend to have lower resistivity, making them better conductors. Conversely, dry, sandy soils tend to have higher resistivity, making them poorer conductors. The depth at which the ground rod is installed also affects its effectiveness. Ground rods should be installed deep enough to reach moist soil. In areas with dry climates, it may be necessary to install longer ground rods to reach adequate moisture levels. In addition to ground rods, other types of grounding electrodes can be used, such as ground plates and concrete encased electrodes, also known as grounds. Ground plates are typically made of copper or galvanized steel and are buried in the ground. Grounds consist of a bare copper conductor encased in concrete. These types of grounding electrodes can be more effective than ground rods in areas with high soil resistivity. When testing the grounding system, it is important to use calibrated equipment and follow proper testing procedures. The clamp on ammeter should be calibrated regularly to ensure accurate readings. The testing should be performed under normal load conditions to simulate the flow of current during a fault. It is also important to take multiple readings and average them to account for variations in the load and the soil conditions. The information gathered from ground rod testing can be used to identify potential problems and make recommendations for corrective action. If the resistance to ground is too high, the ground rods may need to be replaced or supplemented with additional electrodes. If there is evidence of corrosion, the ground rods and connections should be cleaned or replaced. If the soil conditions are poor, the soil may need to be amended to improve its conductivity. In addition to improving the effectiveness of the grounding system, these measures can also help to prevent electrical shock and fire. Grounding systems are critical for electrical safety. A properly installed and maintained grounding system provides a low impedance path for fault current to return to the source, helping to trip over current devices and clear faults quickly. This reduces the risk of electrical shock and fire. Regular testing and maintenance of the grounding system is essential to ensure its continued effectiveness. By following the guidelines and procedures outlined in this information, one can help ensure that electrical systems are safe and reliable. Understanding the principles of grounding and bonding is fundamental to electrical safety. Grounding refers to the connection of electrical equipment and systems to the earth. Bonding refers to the connection of metallic parts of an electrical system to create a continuous electrical path. The purpose of grounding is to provide a low impedance path for fault current to return to the source. The purpose of bonding is to minimize voltage differences between metallic parts of an electrical system. Both grounding and bonding are essential for electrical safety. The NEC provides detailed requirements for grounding and bonding. These requirements are designed to ensure that electrical systems are installed and maintained in a safe and reliable manner. It is important to follow the NEC requirements when installing and maintaining electrical systems. Improper grounding and bonding can create a serious safety hazard. In addition to the NEC requirements, there are other industry standards and best practices that can be followed to improve the safety and reliability of electrical systems. These standards and best practices cover a wide range of topics such as ground rod installation, grounding electrode conductor sizing, and bonding techniques. By following these standards and best practices, electrical professionals can help ensure that electrical systems are safe and reliable. It is important to stay up to date on the latest developments in grounding and bonding technology. New products and techniques are constantly being developed to improve the safety and reliability of electrical systems. By staying informed about these developments, electrical professionals can provide their customers with the best possible service. Remember to consult with a qualified electrician or electrical engineer for assistance with any electrical work. Electrical work can be dangerous and should only be performed by qualified professionals. By taking the necessary precautions and following the appropriate guidelines, electrical systems can be installed and maintained in a safe and reliable manner. In summary, testing ground rod function by measuring current flow in the neutral, GEC, water pipe, and other electrodes provides valuable insights into the impedance of neutral return paths. It aids in identifying corrosion and evaluating the effectiveness of the grounding system, contributing to enhanced electrical safety.